All right. So we have one more section to cover, and then on Thursday, we're going to review for exam number 2. So exam number 2 is just a whole bunch of crazy derivatives. Um, Topping off with exponential and logarithmic derivatives, and we can also use log properties to take really ugly functions and turn them into easier to look at functions for taking the derivative. So we got a bunch of different examples to try to push through. So e to the x is the laziest derivative because when you take the derivative, it's e to the x. So if it's a chain rule setup, e to some ugly function, we'll get the same e to that ugly function times the derivative of the ugly function. So this is just our chain rule showing up. We do the derivative of the outside times the derivative of the inside. So if we're looking at the y equals e to the ax, where a is a real number. So this is just some constant times x. Then our derivative is going to be the derivative of the outside, which is the thing itself again, e to the ax times the derivative of ax. So this is just a constant times x, so like 2x or 5x. So what is the derivative of ax? Yep, just a. So because the derivative of e to the x is itself, this function actually ends up showing up a lot in differential equations. It has a lot of applications. It's also got a lot of nifty uses in statistics even, e to the x and its inverse natural log x. All right, so if we're looking at this ugly function, y equals e to the tangent of 2x, we're going to do our derivative. So we're doing the derivative of e to the something is e to the something times the derivative of the something. Now, the derivative of tangent, we got a little reminder over here, but you're going to have to remember these for the exam. The only derivative formulas that we're giving y'all is the derivatives of the inverse trig functions. But the derivatives of just the trig functions, you're going to have to remember. Sine, cosine, tangent for sure. So derivative of tangent is secant squared. So this is going to be secant squared 2x. And then one more chain rule. The derivative of 2x is just 2. So there is our full derivative. I mean, we could clean it up a little by writing the 2 all the way in front, but meh. It's easier for me to grade if it's strung out like this. So questions so far on doing our derivatives of e to the x? All right, now we got a slightly different one. We've got y equals a to the x, where a is some positive number. So it could be like 2 to the x. It's a very common exponential. So all I know right now is my derivative of e to the x. So when we're looking at the power rule is x to a number. So the x is the base. But it's a great question because that's like a really common, like before it was just move the power down, subtract 1. So the difference is like where the x is. Like when we look at e to the x is now the exponent and e is the base. So that's what's making it different. So our y equals a to the x. We need a way to rewrite this as e to the x. So this is where e to the x and its inverse, natural log of x, are going to come into play. So if I have a function and its inverse nested together, they undo each other. So I'm going to shoehorn both of those functions into this. So I have my y equals a to the x. So I put e to the something and I put natural log of something nested together. So like algebraically, this is the same as our original function. Looks ridiculous, but it is the same. Now I'm going to use my log rules inside here. The natural log of a to the x is just x times the natural log of a. Because natural logs take the power, bring it down in front of the log, and multiply. So natural log of a now, a is just some number, some constant. So the natural log of a number is itself a number. So this is now x times a number. It's a weird number because it's natural log of a, but it's a number. So now our function y equals e to the x times natural log of a, now I can do my derivative, which is just the e function itself again, ex to the natural log a times the natural log of a. Now my ex natural log a, though, was still just my original a to the x. So this part here I can rewrite as a to the x. All right. Sorry, I forgot to write dy dx. This is still y. This one is dy dx. So our derivative of an exponential e to the x is just e to the x. The derivative of any other exponential is the same exponential times the natural log of that number. So even our non-e to the x's are still pretty lazy derivatives. They just get multiplied by this extra constant. So yeah, the derivative we just proved is written here to the side as a formula. So the derivative of a to the x is a to the x times the natural log of a. All right. So we got our weird function, y equals 4 to the 6x plus 6x to the fourth. So this question like really highlights the difference between the two. So the derivative of 4 to the 6x, that's an a to the ugly. So we're going to use our derivative of a to the x, but we're also going to use a chain rule in there. So it'll be 4 to the 6x times the natural log of 4, but also times the derivative of 6x, which is 6. Plus, then our derivative of 6x to the fourth will be 6 times, and then x to the fourth, we bring the power down, so it's 4x to the third. We could clean that up a little, but not much. All right. Now we're going to shift into thinking about the derivative of the inverse of e to the x. So the inverse of e to the x is natural log x. So we derived this funky formula for the derivative of the inverse. It's 1 over the derivative function of the inverse of the thing. So our derivative of natural log x is 1 over. Now the derivative of the normal function e to the x is e to the x. So e to the, and then we put the inverse function inside here. But e to the natural log of something, e and natural log cancel each other out. So we actually end up with the derivative of the natural log is 1 over x. So not quite the laziest derivative, but pretty lazy. Now I write my natural logs with a capital L because if I write a lowercase l, it looks like 1n or in, and it just gets confusing and with like me looking at my own work. So I habitually write natural log capital Ln just so it's very distinct. So now we're going to practice this derivative. So our derivative of ln x is 1 over x. So if we have a chain rule, the derivative of natural log of ugly is going to be 1 over ugly times the derivative of ugly. So we'll have an ugly on the bottom and the derivative of ugly on top. So this particular format is actually going to show up fairly often when you're looking at antiderivatives in Cal 2. So you want to get really comfortable doing derivatives now, so that way you can look at them inside out and backwards for Cal 2. So let's try it out, see what we get. So the derivative of the natural log of x to the fifth. Now there's actually two ways to think about this, but let's just go the straightforward, use our derivative rule. So the derivative of natural log of ugly is 1 over ugly times the derivative of ugly. Well, the derivative of x to the fifth is 5x to the fourth. But now I see there's an x to the fourth on top and an x to the fifth on the bottom. I can reduce that, so I end up with 5 over x. Now, if I look back at the original function, the natural log of x to the fifth, what do natural logs do with exponents? So log's whole purpose in life is to do this thing to exponents. So logs take powers and bring them down up front. So our function, the natural log of x to the fifth, is the same as 5 times the natural log of x. And then we can do the derivative of this reduced function, and we'll get the same result. It's just 5 is a constant times the derivative of natural log x is 1 over x. So there's the same 5 over x. So because of logs' natural ability to deal with powers, they can also deal with products and quotients. Using the log function is actually a way to get around having to use a quotient rule and a product rule on a really nasty function setup. But, ugh, here's the kind of stupid function we put on a test. I hope not quite this ugly, but it's not impossible. So on the test, you will get this. Like that'll be on the formula sheet. All 6 of the derivative of the inverse function, inverse trig functions will be on the formula sheet. You're not going to use all 6 on the test. Maybe 1, maybe 2. I don't remember. I haven't looked at the test since spring break. And I had a lot of sleep then. All right, so we're going to do our derivative here. Just write f prime of t. So the derivative of tangent inverse of x is 1 over 1 plus x squared. Or tangent inverse of thing is 1 over 1 plus thing squared, and then times the derivative of thing. So I have 1 over 1 plus the natural log of t squared, whole thing squared, ick. times the derivative of the natural log of t squared. Well, the derivative of natural log of something is 1 over something. And then times the derivative of that something, which would be 2t. Now this natural log of t squared, whole thing squared, doesn't simplify. Like the natural log can't interact with that square on the outside. So I could, inside there, the natural log of t squared, I could write that as 2 natural log t. And then I could square the 2 on the outside, but the natural log of t being squared like is stuck like that. So I'd just write it like that. All right, so our log properties. If I have the log of a product, I can split that into the log of the first thing plus the log of the second thing. Where the two things were being multiplied, now it's the sum of 2 logs of the things. So likewise, the log of a quotient, x divided by y, is going to become log x minus log y. Our middle rule here is log's whole purpose in life, to take the power, bring it down in front of the log. And then the last two are just using change of base formula. And we really only bother to use change of base if they give us a log base that's not natural log. So looking at our setup here, the derivative of x times y or the derivative of x over y, that requires using the product or the quotient rule. But the derivative of natural log x plus natural log y, oh, that's just 1 over x plus 1 over y times the derivative of y. So making use of our log properties, we can do a derivative of that. So look at that function, the square root of t plus 5 divided by t to the 5th times cosine of t. So as it is, that's a quotient rule that has a product rule on the bottom and a chain rule on top. Horrible mess to try to do the derivative of directly. So when we're going to use logarithmic differentiation, what I'm going to do is take the natural log of both sides of the equation. So I'm not taking the derivative yet. I'm just applying the natural log, and I'm going to clean it up, and then I'll deal with the derivative. So we have the natural log of y equals. So the natural log of a quotient, top minus bottom, so natural log of square root of t plus 5 minus the natural log of t to the 5th cosine t. Now our t to the fifth cosine t, that's a product. The log of a product, I can split this into two different logs. But this minus sign in front is going to apply to both of those. So this becomes minus the natural log of t to the fifth plus the natural log of cosine t. And then still with our natural log of t plus 5, or square root of t plus 5, sorry. Although I'm going to rewrite this. The square root of t plus 5 is t plus 5 to the 1/2. Because our other big thing natural logs do is deal with powers, so we're going to use that to deal with powers. But this minus sign here needs to get distributed through. So right now we're still doing algebra. We haven't actually taken a derivative. So I have 1/2 times the natural log of t plus 5 minus, so this is minus from the minus being distributed, but then this power can come down in front. So it's minus 5 natural log t and minus the natural log of cosine t. So now that I've strung it all apart, it's now a bunch of sum and differences. I've pulled my powers down. Now I'm going to take the derivative. So our function is written in terms of t, so we're taking the derivative with respect to t. So the derivative of natural log of y is 1 over y times the derivative of y. So we're actually using implicit differentiation here. Now our derivative of 1/2 times will still be 1/2 times. The derivative of natural log of t plus 5 will be 1 over t plus 5 times the derivative of t plus 5 is just 1, because derivative of t is 1. The plus 5 derivative of 5 by itself is 0, so it's just times 1. Minus 5. The derivative of natural log of t is just 1 over t. Minus the derivative of natural log of cosine t will be 1 over cosine t times the derivative of cosine is negative sine. Now, I haven't gotten the derivative dy dt by itself. I've got this 1 over y bullshit here. And I'm going to clean up my strung out derivative sum. So this 1/2 times the t plus 5, I'm going to distribute that 2 through, so that is 1 over 2t plus 10. This becomes minus 5 over t. Then this minus negative becomes plus, and sine over cosine is actually tangent. Now I need to get dy dt by itself. So right now it's 1 over y times dy dt. So I'm going to multiply by y, which means I'm taking the whole entire right side and multiplying by y. So dy dt equals the 1 over 2t plus 10 minus 5 over t plus the tangent of t times, and then it's y, so I'm going to go back and just copy what y was. The square root of t plus 5 all over t to the 5th cosine t. That's our derivative. So logarithmic differentiation, when you've got a really disgusting looking function, the log takes the ugly product quotient and powers and strings it all out into sums and differences. It's a lot easier to do the derivatives of sums and differences than it is to do the derivative of products and quotients. So I'd say this is a little less complicated than doing the derivative of the original function, but you've got to be comfortable with using your log rules. So what questions do y'all have on this crazy mess? All right. Yep. Actually, I'm trying to remember if we put a logarithmic differentiation. Like using the derivative of natural log, that'll absolutely be on the test in several spots. But one where you want to use logarithmic differentiation, probably not. Certainly not one this ugly. That function is just stupid. It's just there's a lot of anti-derivatives that make use of natural log. So you want to get practice using the log properties, being able to think about problems from this perspective. All right, and then sometimes we get functions like this, t to the square root of t. So trying to do the derivative of that, I've got a formula for the derivative of variable to a power. I've got a formula for derivative of number to a variable, but I don't have a formula for the derivative of variable to a variable. So the only way to even start attacking this is to use a natural log on it. So natural log takes whatever the power is, brings it down up front. So I've got the square root of t times the natural log of t. So now this is an annoying product rule, but now this is something I can take the derivative of. So we're taking the derivative with respect to t. So the derivative of natural log of something is 1 over something times derivative of something is dy dt. All right, square root of t, I'm going to come back in here and change that to the 1/2 power. So we have t to the 1/2 times the natural log of t. So we have to use a product rule for our derivative here now. So product rule is derivative of one thing times keep the other the same plus, and then do it the other way around. So I'm going to do my derivative of t to the 1/2. That'll be 1/2 t to the negative 1/2. And then that's still times the natural log of t. Plus, now we keep t to the 1/2 the same. And now we're going to do times the derivative of natural log of t. Derivative of natural log is 1 over the thing. Our thing is t. The derivative of t would just be 1. So there is our current dy dt. Well, 1 over y times dy dt. All right, so we could write this as the natural log of t over 2 t to the 1/2 plus the t to the 1/2 times 1 over t. That's 1/2 minus 1 would be the negative 1/2, or I can write it as 1 over t to the 1/2. So I could even, by multiplying by 2, write this as one big giant fraction if I wanted. I'm just going to leave it like that, though, but we do have to do the 1 over y part. I got to multiply by y on both sides. So the natural log is a very powerful tool that we can use as long as we're careful about how we use it and remembering all of our log properties correctly.
Are there log properties on the test? Okay.
No, you got to remember the log properties. I was worried about getting through the whole thing, so kind of rushed it, and whoosh, we finished the whole thing very quickly.
How is t to the 1/2 multiplied by 1/t, 1/t to the half?
So when we have t to the 1/2 times 1/t, I can think of this as t to the 1/2 over t to the first. And then when you have it like this, the power subtract. So it is t to the negative 1/2, and then I rewrote it as 1/t to the 1/2. So are there any questions from the homework that have been like lingering, bothering y'all?
We just have to remember all those properties.
I mean, it's really the first three. We're not gonna use the change of base or the last one. So just the log of a product becomes the sum each with a log of a quotient becomes a difference each with a log, and then logs bring powers down in front. So if you run through a couple problems of logarithmic differentiation, you're going to have to use those properties over and over again. But on the test, I don't think we're actually going to give you a problem where you have to solve it using logarithmic differentiation. So this is more just like practice it because it's a skill that's good to practice, but the skill itself is a little too long for the test. Like I just looked over the test from last semester and we didn't put a logarithmic differentiation on there. Now, there is a problem or two where if you remember your log properties, you can make the problem a little simpler, but the problem is not that much more complicated if you don't do it. Like when we did this one, the natural log of x to the fifth, like doing the derivative of this was not that bad. If you remembered the log properties, the derivative was nicer, but not that much different in terms of the amount of work. Sorry, I'm just flipping through the exam 2 practice problems.
Is it open already?
Mhm. So yeah, we did put a logarithmic differentiation problem in the exam 2 practice problems, but it's not on the test. It's actually like very, very similar to this one here. Just the like it's t plus 7 and I think it was like a different t power, t to the 8th cosine t, yeah. So most of the exam is going to be doing weird derivatives. All right, so this is the practice problem number 4. So this one sometimes throws people for a loop because we have a table with information that we're going to use in the problems here. But we did put this format on the test. All right, so like we're going to calculate the derivative and then we're going to use the table. So initially just ignore the table, focus on each question. So our first question is if h of x is x times f of x plus 4 times g of x, then figure out what h prime of 1 is. All right, so we're going to ignore the fact that it's saying of 1. We're going to focus on just finding that derivative. All right, so finding our derivative. When I have x times f of x, that is a product. So I got to use my product rule. So my derivative of x is 1 times keep f of x the same plus now keep x the same times the derivative of f of x. So I write f prime of x. Plus, now the derivative of 4 times g of x Well, 4 is just a constant, so that just carries through. So we'll have 4 times g prime of x. So I found my formula for the derivative. So questions on that part? All right, now they told us to find h prime of 1. So my function notation, I've put a 1 in place of the x, so I'm going to follow through on all the rest of it. I'm going to put 1 in place of the x. So this is still 1 times, but now this is f of 1 plus 1 times f prime of 1 plus 4 times g prime of 1. All right, now I'm going to go back and use the table. So I'm going to do a little screenshot of the table. All right, so since we're looking at h prime of 1, I'm going to focus on the column where the x value is 1. So when they ask for f of 1, f of 1 is -8. F prime of 1, that's df dx at 1, that is 6. And then g prime of 1, dg dx at 1 is 0. So we end up with -8 plus 6 plus 0, so that is -2. So we had to apply our derivative formulas. We had to use the product rule. We had to remember the constant multiple rule. And then we had to use the table.
Between the constant product rule on the four and the event.
So anytime we have just a number multiplied to a function, the number just carries through to the derivative. So like if you look at this and think it's a product rule like the first time, you could still treat it as a product rule. It's just in the product rule, you'll do the derivative of a constant is 0. So the like other half of the product rule ends up being 0. So if your brain accidentally does it that way, like it'll still work. So it'd be like 4 times g prime of x plus derivative of 4 is 0 times g of x. So the 0 times g of x is 0 plus 0. We don't have to write it. So you'll still end up with 4 times g of x, g prime of x. But it's also like, yeah, just that. All right, let's take a look at number 4 on this one. It's got a quotient rule and a 1 over x. So remember, 1 over x, we could rewrite as x to the negative 1 power. So now it's set up in a way we can use our power rule. But then plus g of x over f of x, we're going to have to use a quotient rule on that, but the functions are like backwards order from the way we normally write it. So try out finding the derivative of this. So see if you can remember the quotient rule after spring break. That's the hard ask. All right, so do that later. All right, so our power rule will be negative 1 x to the negative 2 plus now our quotient rule. So quotient rule is low d high. So low is f of x times d high is g prime of x minus high d low, so g of x times f prime of x over square the denominator, so that's f of x squared. So that is our derivative. Now we're going to fill in, we're doing h prime of 4. So everywhere there's an x, I'm going to write a 4. So I have negative 1 times 4 to the negative 2 plus f of 4 times g prime of 4 minus g of 4 times f prime of 4 all over f of 4 squared. All right, so we're now looking at the 4 column. So my f of 4 is 1. All right, so this -1, 4 to the -2 becomes -1 over 16. All right, so f of 4 is 1. G prime of 4, dg dx at 4 is a ridiculous 54. All right. G of 4 is also 54. All right. And then f prime of 4 is a 0. So we get -1/16 plus 54. And I'm pretty sure if I type that, Webwork will take it like that. Yeah. Now you could calculate it, write the decimal and type in the decimal and Webwork will take the decimal, but so what questions do y'all have on how this one shook out? All right, let's try this one. It's a little cute practice with what we learned today. right, so negative 6x to the 7th times e to the x. So that is a product rule. So I'm going to do the derivative of negative 6x to the 7th. That'll be negative 6 times 7x to the 6th. And then we keep e to the x the same. Plus, now I keep negative 6x to the 7th the same. And I multiply by e to the x, the derivative of e to the x rather, which is e to the x. So I have negative 42x to the 6th times e to the x minus 6x to the 7th times e to the x. So we got the e to the x showing up in more than one spot there. All right. Well, we had a bit of a spring break, so I'm good calling it there.
Next couple days, just